Thanks for inviting me to give this talk. It's going to be a little bit more futuristic than the previous talk. So no experiments yet, but hopefully our speculative ideas can motivate some future experiments. That's the plan here. So the talk is about our proposal to use antiferromagnet-based heterostructure for neuromorphic applications. So the specific questions I want to address here is the following. Can nail easy plane winding dynamics in a patterned antiferromagnetic heterostructures be exploited as building block for neuromorphic hardware? The work was done by my postdoc mostly, Susie Zhang. And all right. I will give you, okay, let me actually show you the specific paper that this talk is mostly based on. I will not deviate much from this paper. So if you get intrigued by our proposal, all of the details can be found here. So let me start with motivation, open questions. I mean, the motivation is obvious. There's a lot of, lots of ideas, lots of utility for machine learning these days, particularly unsupervised machine learning. The impression that is easy to get, however, is that things are somewhat lacking on the hardware side. I mean, the hardware that we have available now is mostly designed with digital computing in mind. So the natural question that comes to mind, can we use other types of physical phenomena to think of hardware that would be more naturally adaptable to machine learning, so brain-like behaviors? And magnetic systems very naturally come to mind in that regard. Specifically, I'll make the case that topological magnetic textures that transport in dynamics, focusing on insulating materials in particular, appear to provide all of the conceptual building blocks that are needed for neuromorphic applications. I will, and then of course different angles, different approaches to neuromorphic applications. In this talk, I will really focus on sort of really brain-inspired situations, the so-called spiking neural networks, where you have neurons, axons, dendrites, synapses. So really, we're trying to imitate brain as closely as possible. And it seems that topological magnetic texture, transport and dynamics have all of the necessary ingredients for that, such as solitonic signal propagation, nonlinear signal integration, plasticity. I will comment on some related ideas that we have for energy storage that even further make the case for the system, because we can have delocalized energy stored within the same hardware. What are the questions? Well, I guess the key open question is, well, can any of this, all of this be realized experimentally? So at this point, these are just very speculative ideas, even with the basic aspect yet to be demonstrated. So that's where most of the open questions lie. Is it well, before you even ask if it's practical, can we demonstrate the physical phenomena that go into these ideas, and then ultimately, how practical is it? Okay, so the keywords, so the key things I'm underlined here. So I'm talking about spintronics-based hardware implementation of neuromorphic computing, really brain-like neuromorphic computing, based on spatial temporal interconversions of magnetic winding. Let me explain what I mean by this. That's really the key to the whole talk. So let me start with a little cartoon. that shows the key building blocks. So as key building blocks, I have interconnects as of quasi one-dimensional wires. Some of them will serve as inputs, some of them will serve as outputs. Throughout this discussion, think of two-dimensional planar geometry. So I have a top view on a two-dimensional geometry. Moreover, within this spatially two-dimensional geometry, magnetic configuration is going to be primarily easy plane. So this is a top view on some kind of easy plane winding dynamics of antiferromagnetic order parameter. The interconnect carries such a dynamic winding texture. So this interconnects to the two interconnects here will behave as axons supplying some kind of signal, and there could be many of them. Then I have a monodomain neuron that integrates this incoming signal, and then under certain conditions that I will discuss later, it can reach a threshold, fire. Firing means simply switching, simply ticking by pi. So you switch by pi. Of course, if an antiferromagnet switches by pi, angle pi, it goes back to its original configuration. That switch triggers a solitonic signal in the output, because you switch order parameter orientation by pi at the boundary that triggers an outgoing soliton that carries angular winding of pi. So such easy plane angular winding is quantified in terms of the so-called winding charge. I'm going to refer to it also as topological charge, which is defined simply as spatial gradient of the winding angle. It's normalized by pi for convenience. So here we see a little lump of topological charge, or winding charge +1. There's another lump of charge 1. You could anticipate that the lumps will eventually behave as solitonic objects. Here that the winding charge is somewhat delocalized. Maybe there is a soliton, maybe not, maybe some kind of thermal fluctuation taking place. Maybe it's not so clear if there are quantized lumps or not. Nevertheless, there's still some kind of delocalized winding charge that may undergo some dynamics here, maybe some thermodynamics. This lumps will be triggered ultimately by some kind of external inputs and propagating from left to right. So I will suppose, let's say, in one of these interconnects, I have some kind of flow of a bunch of such lumps with a specific chirality. The chirality corresponds to the net winding charge carried by the texture. You could imagine that if you turn on some kind of interaction here between this monodomain and this wires, this chirality of the lumps impinging on this monodomain, what I'm going to call a neuron, will trigger neuron dynamics, will stimulate neuron dynamics, monodomain dynamics, also with a particular chirality. So this spatial chirality of the incoming signal will translate into temporal chirality of this monodomain dynamics. And eventually this temporal chirality may integrate the incoming signals and result in a sort of neuronic type of triggering. Okay, this is now an artistic picture of sort of the ultimate dream schematic. Like I said, these monodomains will behave as neurons. All of the functionality here is based on spatiotemporal winding dynamics. Okay, so the neuron is ticking by pi at a time when its dynamics is triggered. The axons here are the outputs, which send a solitonic lump of winding charge of pi. It propagates. The solitons can propagate. In the ideal limit, they behave as relativistic particles according to Sine-Gordon equation that describe one-dimensional easy plane antiferromagnetic dynamics. So they propagate. They could fan out. after fanning out, this solitons are impinging on a system that imitates a synapse. So there is certain memory that again is realized through a winding characteristic of some antiferromagnetic region. As I will discuss later, the synapse will be treated as a sort of a thermodynamic system containing winding. So I will characterize within the synapse winding with certain temperature and certain chemical potential associated with the topological charge. So that will contain sort of memory and the information about your learning outcome. It will be supplied by an external source that is again a lump of wound up antiferromagnetic texture, in which the winding charge, the topological charge of winding, is associated with some fixed chemical potential. So that's the chemical potential of the topological charge, which is now maintained by some external sources. That will power the whole dynamics, power, amplify, whatnot. So this external source of winding with fixed chemical potential, that will be the only sort of interface with the outside world for the purpose of sort of feeding the system. Okay, so you have it's like a battery that fits the system, and of course you have inputs that collect information from just like how our vision or various senses work. Then this winding keeps going. There's dendrites that transmit the signal further. There's now a weak link between the dendrite and a neuron. So the winding supplied by all these dendrites through the weak links now get integrated. So many solitonic inputs are needed to trigger this switching of the neuron, and then the process keeps going. Okay, then we implement the so-called spike timing dependent plasticity, so that's supposed to imitate again how our biological neurons work. So depending on the timing of the post-synaptic neuron relative to the presynaptic neuron, we then have a feedback mechanism that changes the weight of the synapse, and that weight is parameterized by the chemical potential of winding. So that's kind of the dream idea that summarizes our proposal. Of course, this is like a purely artistic sketch. So now in the rest of the talk, let me step through some specific physical ingredients that go into implementing this kind of fantasy. What is a fantasy at this point of time? Okay, so now let's go to the basics. Hopefully this will be useful, especially for the students in the audience. So now I'm kind of switching my mode to just like just doing basic physics of one-dimensional easy plane antiferromagnetic dynamics. First, before writing down any theory for the antiferromagnet, I start with the topological continuity equation for the winding density. This topological continuity equation precedes any specific physical considerations. With physical considerations, I mean things that have to do with energy and symmetry. So that provides, this topological conservation law provides sort of the overarching structure based on which the whole functionality is built up. Now let's dig into the specific physics. As a concrete model, we'll start with this kind of minimal Hamiltonian with the stiffness energy, some easy plane anisotropy energy. So M here is out of the easy plane magnetic density, spin density. So phi is the easy plane nail orientation. M is the out of the easy plane spin density, which is canonically conjugate variable. So if later on I'm going to treat phi as like a variable in a sense, and m is sort of momentum, canonical momentum associated with that variable. The canonically conjugate, the curly brackets here stand for the Poisson bracket. If you quantize it, quantum mechanically, that would become a commutator. But everything we're going to talk about today is going to be classical. So I'm going to develop classical theory, starting with this Hamiltonian, starting with canonical conjugacy, this Poisson bracket between a winding variable and the spin variable. This is now some additional anisotropy within the easy plane that will define my sort of the solitonic clumps that carry quanta of sort of classical quanta of information. Furthermore, we introduce damping in the standard fashion through Gilbert damping in the system by complementing this Hamiltonian with this Rayleigh dissipation function parameterized by the dimensionless parameter alpha that will eventually be interpreted as Gilbert damping associated with Néel dynamics. Okay. So let's see. All right, so let's see how much time do I have left. Actually, 3 minutes. Okay, before talks. Okay, so the rest, let me just step through, the basic physics ingredients deriving from this model. We construct Sine-Gordon equation without damping. The basic elementary degrees of freedom that are relevant to us are solitons, which behave as relativistic particles. Now, at the edge of such a one-dimensional system, I will be interested in how such solitons interact, for example, first with an adjacent metal. So as a soliton impinges on an interface between, let's call it a dendrite and a metal, this metal will act as an interconnect, let's say to a neuron. The soliton, this transmission of the soliton is kind of digital in a sense. So the soliton can either get transmitted, fully transmitted, or fully reflected. There's no other possibilities in between, again, because of topology. Because in the end of the day, when the dynamic settles down, the angle of the Néel orientation at the boundary will flip by 0 degrees or by pi, by angle 0 by angle pi at the end of the day. So changing by angle 0 will correspond to no transmission of the soliton, changing by angle pi to the full transmission. Then you may ask, well, can the solitons, what are the conditions for the soliton transmission across the interface? Putting together spin pumping associated with adiabatic magnetic dynamics at the interface and the exchange boundary condition, we conclude that at a certain velocity, when these two terms are equal, at a certain velocity, there's sort of impedance matching condition, so the soliton gets transmitted perfectly, and at a range of the velocity near this perfect velocity, like I said, because the transmission is digital, again, the soliton will get transmitted perfectly. The perfect transmission of the full soliton transfers winding pi into the metal, which translates into spin current. The spin current corresponds to just accumulated spin pumping, which again, if the angular change is overall pi, that the amount of spin current is quantized, some particular quantized quantity per soliton that gives a torque kick on the neuron. Now, from the point of the neuron, the same Sine-Gordon type of description applies, except that the dynamics is monodomain, so we don't have the texture term. Other than that, it's exactly the same. The same kind of equations, which can be interpreted in the monodomain case as damped dynamics of a particle through a washboard potential. Each soliton kick gives you a kick up the washboard potential, and then eventually, if enough solitons kick you within a given amount of time at a certain frequency, you can overcome that forward potential and trigger the neuron. So that very nicely imitates so-called leaky integration and fire dynamics of neurons. Again, in terms of mathematics, phi is the monodomain angle within the easy plane. M is the total out of the easy plane magnetic moment of this neuron. So the susceptibility plays the role of the inertia. So the magnetic moment is just the canonical moment conjugate to phi. This is the inertia term. So you could see damping is like viscosity. So it's really just viscous dynamics through a washboard potential. It seems like a very nice realization of leaky integration and phi. I don't have time to talk about the synapse, but like I said, the key is that again the starting equations are the same, Sangorian equation, but I specialize this equation now to a thermodynamic limit. Have an ensemble of many solitons forming a solitonic liquid that I describe thermodynamically in terms of chemical potential, and it is that chemical potential of the solitonic liquid that is my learning weight. That is been adjusted depending on the relative time of the post-synaptic neuron relative to the presynaptic neuron. That's it. So this is the summary. Again, no time to dig into the details of the plasticity that concerns changing of that chemical potential of the synapse, but you could find more details in our paper, as I've already said. Again, as a side remark, there is a very compatible idea for energy storage, which concerns maintaining this external chemical potential of mu, external chemical potential of the winding density at some given level mu naught, which is fueling the whole process. So that sort of completes the whole picture, and please take a look at some take-home messages, and I still have a couple of minutes for questions. Thank you for your attention.